Dear ladies and gentlemen, hello everyone. I am very pleased to introduce this webinar presenting Soitec engineered substrate for 5G. I am Bernard Aspar, Senior Executive Vice President of Soitec, managing the Global Business Unit organization. Today, I am very pleased to be joined for this presentation by the Soitec Business Unit Manager, having in their product portfolio some key substrates enabling 5G technology. So with me, we will have here Jean-Marc Lemay, Head of RF-SOI Business Unit, Michael Rea, in charge of FD-SOI Business Unit, Mariam Germain, Head of EpiGaN BU, and Christophe Didier, responsible for Filter Business Unit. The purpose of this webinar is to give you an overview of engineered substrate playing a key role in enabling solutions for 5G, both on terminal and handset side, as well as infrastructure. I will first introduce the comprehensive offer of Soitec engineered substrate that have specially designed to answer to the challenging requirement of 5G by collaborating with the anti-RF ecosystem. Then my colleague will describe more in details 4 different product lines, namely RF-SOI substrate, FD-SOI, EpiGaN, and piezo on insulator substrate. Finally, after the closing remark, we will have 15 minutes of Q&A. All of you heard many times about the benefit of 5G network and the tremendous technical improvement it represents comparing to 4G standards. Today, we are going to discuss the critical role of engineered substrates which are enabling this technology. These substrates are enabling both performance and cost of ownership. They are the foundation of the 5G smartphone and base station, but also the substrate will play a key role in other segments such as IoT, automotive, and the Industry 4.0. At Soitec, we have been designing engineered substrate for more than 25 years. To design the right substrate able to meet the expectation, we are working closely with the entire value chain. First, by listening and understanding the requirement of our direct customer, which are mainly the foundries. Then, by collaborating with their customer, such as RF front-end module makers or chipset fabless, and also by discussing closely up to the phone makers. We are also part of many consortia, and we are anticipating the needs by working with a wide range of R&D centers at global scale. By collaborating with the leaders of the entire value chain of this industry, we have designed different engineered substrates to build key circuits for smartphone, 5G base station, and other connected devices. Today, some of these substrates became the industry standard for front-end module. RF-SOI is the best example. Then we have our FD-SOI substrate, who present many advantages to integrate different functions on the same die. Our photonic SOI is becoming also a standard for silicon photonics, for server of the cloud. Then we have our new generation of substrate, such as epitaxy gallium nitride wafers on silicon or silicon carbide. Finally, by working closely with the key players, we have designed a new substrate called POI, for piezo on insulator substrate, which is now ramping in high-volume manufacturing. Soitec is not only designing new products, but we are delivering this product in high volume thanks to our manufacturing footprint across the world. In summary, we have a capacity able to reach close to 2 million SOI wafers per year in 300 mm. In 200 mm, with our Bernin 1 fab in France and our partner Singhu in China, we are able to deliver around 1.3 million wafers per year. For our new generation of non-silicon-based engineered substrate, we are also growing our capacity with facility installed able to reach 500,000 of wafers for POI in 150 mm. And finally, in Belgium, we have our EpiGaN manufacturing location. Today, the front-end module is a key element of 4G and 5G system. Before describing where our substrates are bringing value, let's highlight the key components involved in the front-end module. You have different switches, low noise amplifier, power amplifier, supply moderator, antenna tuners, and filters. We have summarized on this slide the comprehensive offer of engineered substrate. It is like a menu à la carte. Depending on the requirement for building some specific devices, you can choose the right substrate adapted to your need. This is true for both 5G sub-6 GHz and 5G millimeter wave. If you look at the first table relative to 5G sub-6 GHz front-end module, you see that RF-SOI is a perfect product for switches, integrated linear, antenna tuner. RF-SOI is a standard of this industry for this device. For new generation of filters, we have our POI substrate, which is getting a lot of traction in the market. Then we have FD-SOI substrate, who are also well adapted for envelope tracker. Then, if you look to the table for 5G millimeter wave, you could see that FD-SOI is a substrate on which you can integrate on the chip all the function, including part of the transceiver. RF-SOI is also very well suitable for millimeter wave solution, depending on the level of integration that you want. And GaN is well adapted for base station and smartphone. These substrates are the foundation for all devices that we mentioned, and they are becoming essential. The proof is that when you look at the content of this substrate in the smartphones, you see that the content increased strongly. For example, in average, this means that for mid-end and high-end phone, the RF-SOI content in front-end module increases by 60%, moving from 4G to 5G sub-6 GHz. Then, this content doubles if you add millimeter wave capability to a 5G phone. In this case of millimeter wave capabilities, SOI content can be a mix between RF-SOI and FD-SOI. Same for filters. Between 4G and sub-6 GHz, the average content of substrate for filters doubles too, and a lot of innovation is required to address the performance. So now let's move to the presentation of our product portfolio, and Jean-Marc Lemay will present the first product, RF-SOI.
So thank you, Bernard, for this RF-SOI introduction. So RF-SOI is a Soitec #1 business unit in volumes and revenues. with a strong exposure to the smartphone markets, where RF-SOI is the standard for 100% of the RF front-end modules. So this slide here is showing how RF-SOI is penetrating all the RF front-end devices. So we can say there is no 5G without RF-SOI, which is the substrate of choice for cellular front-end module. We see also that integration is key for RF. More integrations are coming with LNA today and later PA. Actually, as we can see on the plots, 90% market share is obtained on antenna tuners, on switches, but also on the diversity LNA. There is still work to do to integrate PA, but also to capture a millimeter wave device. But as 5G brings significant increase of square millimeter, thanks to the sub-6 GHz bands and the 4x4 MIMO pervasions, more integrations will come. We see today already some integrations on new Wi-Fi 6 generations with integrated PA, but also on millimeter wave active antenna system infrastructure, where RF-SOI is the sweet spot for remote radio head. A few words on 5G millimeter wave handsets, which require 3 to 4 modules, such as millimeter wave signal is not blocked by ants or objects. If we start with one band, 28 GHz, and later move to two bands, 39 GHz, and today RF-SOI is already matching the EIRP requirements in terms of power consumptions, and therefore will be a natural evolution to address these forthcoming markets. A few words about RF-SOI market trends and dynamics. Again, as we say, RF-SOI is a standard for smartphone RF front-end module, for switches, diversity pass, and antenna tuners. We see a strong demand in both 8-inch and 12-inch substrates. 8-inch remains solid and in high volumes at all major foundries, while 12-inch demand is growing fast, with major foundries developing their flagship RF front-end technologies on advanced nodes. Soitec is keeping its technology leadership. We are developing new product roadmaps covering both high-end and low-end market segments. The dynamic is coming from the 5G smartphone markets, where we estimate that in 2020 about 200 million units will be sold, 450 million units in 2021, and above 1 billion by 2023. 5G market is requesting more segmentation, from higher performance to cost-sensitive device, with more and more integration, including some digitals. As a matter of fact, 5G smartphones will increase significantly the RF-SOI content. So Bernard explained to us that, for example, on sub-6 GHz, RF-SOI content is increased by 50% compared to 4G smartphones. On millimeter wave, we see strong tractions in active antenna system infrastructure. And on Wi-Fi, thanks to new Wi-Fi 6 and 6E generations, there is new RF-SOI design wins. Beyond the legacy HRSOI and RF-ESI products, Soitec RF-SOI BU is offering an innovative product roadmap to address all these markets that we will cover now. RF-ESI with trap reach has obsoleted legacy HRSOI with Sigbox. RF-ESI is our flagship technology, representing more than 80% of the chip wafers to foundry in 8-inch and 12-inch. It can be differentiated by linearity performance, with figure of merits like second harmonics translated to a harmonic quality factor on substrates. We can tune the high resistivity on the wafer, as well as the thick trap bridge layer, but also the SOI and box thicknesses. I can tell a few words about the function of the trap bridge. The trap bridge allows to kill what we call the parasitic surface condition below the box. We need to remember that the silicon is a non-linear substrate, where harmonics should decrease linearly when the silicon resistivity increases. But on HRSOI, due to the seed box, charges are generated, and this creates a conductive layer below the box. The trap-rich layer role is really to freeze this freeze carrier under the box, preventing conductivity and maintaining the high effective resistivity of the HR substrate. Now let's focus on innovative new RF-SOI substrates. We introduce two new products. On the left-hand side, we have IFAM-SOI. It's targeting low-end, cost-sensitive cellular front-end module, high integration Wi-Fi, connectivity, and IoT. The SOI and trap-rich layers, as well as the manufacturing process and the raw materials, are optimized for cost savings. The substrate options are limited. We provide the substrates in 12-inch. The box and the high resistivity of the substrate wafer are fixed, as well as the trap-rich layer. On the right-hand side, we have the next generation of RF-SOI, which is still in R&D development. It's so-called RF-ESI 100T. It's designed for high-performance sub-6 GHz switch antenna tuners with harmonic stability above 125 degrees Celsius, addressing automotive markets and exploring millimeter wave bands. SOI and trap-rich layers, manufacturing process and raw materials are optimized for high performance and improved cost of ownership. There is different substrate options. We can adapt the linearity and harmonic performance, keeping the temperature stability above 125 degrees Celsius. SOI and box thickness can be fine-tuned, and these substrates utilize low permittivity trap-rich as well as a low resistivity base wafer. The low permittivity materials provide better isolation, especially at higher frequency, then becoming a substrate of interest for millimeter wave bands. In conclusion, Soitec has a long success story with RF-SOI established as a standard for 4G mobile front-end module. New RF-SOI products for 5G sub-6 GHz and millimeter wave are the natural evolution of this success story. I will hand over to Michael Rea, who will present FD-SOI products.
Thank you, Jean-Marc. Whereas RF-SOI has been the natural catalyst for RF applications, FD-SOI has been and continues to be adopted as the low-power platform. Maturity levels in the IP ecosystem are addressed by highlighting the fiscal year 20 products. For example, a 4-chip low-power FPGA platform that targets areas such as edge compute was launched by Lattice Semiconductor. An autonomous driving processor continues to ramp in favor of Intel Mobileye. And smart home technology promoting FD-SOI also as a cost-efficient solution continues to increase in tandem with voice-recognized connectivity. Also, cost efficiency in tandem with low power is also highlighted with the increased adoption in wearable devices, the lattice being in the Casio G-Shock product line. So overall, FD-SOI is both secure and reliable for edge infrastructure and automotive infrastructure. But it is its low power potentials that continue to diversify its adoption. 5G and RF is evolving under similar low power demands, and we expect meaningful gains in 5G infrastructure and UEs, Wi-Fi 6 and radar systems alike. Energy efficiency on a per bit per hertz basis is a key driver, and specifically the energy required to bridge and convert analog and digital domains in excess of tens of gigasamples per second will continue to reduce. Efficient memories, particularly in the embedded space, will come to fruition and will promote advances in automotive products. Of course, this all requires careful progression of Soitec processes from innovation to manufacturing and also including new products. As such, Soitec is aiming to provide next generation of millimeter wave 5G with the novel fully depleted SOI on high resistivity silicon substrate that will spill over into WiGig automotive radar and sub-terahertz designs, including consumer radar. We believe and we see FD-SOI as being the key platform that combines low power with a low-cost gateway to cloud compute architectures required specifically for Industry 4.0 applications. Our foundry partners carry the same vision as Soitec in that connecting the unconnected encompasses readiness in integration, size, robustness, and opportunities to exploit the artificial intelligence realm. These factors are paramount to meeting customer requirements from 5G bandwidth and RF digital integration opportunities through to cost and battery efficiency. For example, instantaneous bandwidths in excess of 1 gigahertz will require readiness in gigasample per second mixed signal front ends, which are reconfigurable to support both millimeter wave and sub-6 gigahertz active antenna solutions. These RF sampling radios fundamentally will be limited by extremely low leakage circuit design techniques needed for switch capacitor data converters, for example. FD-SOI offers best-in-class mixed-signal switch performance and therefore is an extremely efficient means for building low-energy RF sampling radios. To date, key FD-SOI adopters represent meaningful technical leadership in both foundry and in applications. For example, low-power FPGAs for edge applications with the Lattice Nexus platform, through to progressive roadmaps towards 18 nanometer with Samsung foundries, and also vision processors for autonomous driving with Intel Mobileye. This unique mixture of FD-SOI foundry partnerships in emerging platform applications pave the way for an evolution of 5G content. An example of 5G evolution will be witnessed in the form of next-generation millimeter wave, requiring advances in three forms: operational frequency, instantaneous bandwidth, and reconfigurability. Today's systems are addressable using the standard FD-SOI at 24, 28, and 39 gigahertz, but are quickly evolving to next-generation systems that will evolve towards multi-band and multi-user usage, and this will place demands on reconfigurability. For example, in 2023-2024, we anticipate Verizon Wireless in the United States to deploy 1600 megahertz between 37 and 39 gigahertz, in tandem with the 850 megahertz already in use at 28 gigahertz. At the substrate level, Soitec has been developing an exciting technology to meet this evolution on performance and reconfigurability with a high resistivity solution. High resistivity silicon as an RF technology is not novel, and certainly not in Soitec when considering the RF roadmap shown on the left. However, its application to FD-SOI is unique, as it is aimed to potentially reduce power consumption for RF circuits while maintaining digital performance, enhance RF switches, in particular loss at millimeter wave and including linearity, and potentially reducing mixed signal switching noise. So in a typical 5G millimeter wave transmitter shown on the right, at least 6 key performance enhancements are envisioned to be targeted with the goal of enabling state-of-the-art millimeter wave SoC platform. That is, FD on high resistivity silicon is a fundamental stepping stone for FD-SOI evolution and a potentially disruptive technology to enable for next generation 5G, including sub-terahertz applications. Overall, the progression of standard FD-SOI to FD on high resistivity is an example of how Soitec is preparing for increased system-on-chip adoption at the millimeter wave frequencies. And now I'd like to transition to Marianne Germain, who will introduce Soitec innovations in gallium nitride technologies.
Thank you, Michael. Gallium nitride technologies are gaining significant traction in RF and power markets today. They therefore represent a very natural strategic fit with Soitec's current portfolio of engineered substrates. As shown on the left, gallium nitride is the most suited semiconductor for high-power, high-frequency applications. It is becoming mainstream for 4G and 5G base stations. It furthermore offers key advantages over gallium arsenide for power amplifiers in 5G millimeter wave handsets. In the first place, Soitec targets the base station power amplifier market. But we also aim at penetrating the smartphone market with gallium nitride products later on. As shown on the right, both for the 5G infrastructure and the handset architectures, the mandatory attributes for RF power semiconductor devices are high power density, which enables compactness and lower cost. This will also ease the installation of the antenna systems, and high efficiency to ease the thermal management. In simple terms, you need to handle higher power in smaller area more efficiently. And this is exactly where gallium nitride HAM transistors excel. Furthermore, the wide bandwidth performance makes gallium nitride an ideal candidate to enable carrier aggregation to increase bit rates with only 1 MMIC. Thanks to the high frequency capability, gallium nitride is well suited to address new spectrum, such as millimeter wave. And last but not least, gallium nitride power amplifiers also show excellent linearity. To make it short, gallium nitride power amplifiers, regardless of whether they are grown on silicon or on silicon carbide substrate, outperform silicon and gallium arsenide-based technologies in terms of wideband performance, power density, and efficiency. During the rollout of 5G, the increased deployment of small cell antennas will drive demand for compact, highly efficient RF front-end devices. Designers of massive MIMO systems may find it even more challenging to manage power consumption and heat dissipation than the complexity of antenna arrays itself. This means that semiconductor efficiency will become key for MIMO antenna systems, especially at millimeter wave bands around 30 GHz. The graphs on the right-hand side illustrate that for a given output power of the antenna array, gallium nitride is a technology of choice when high power density is needed to minimize the number of antenna elements. This, together with gallium nitride high power added efficiency, is the only way to realize compactness of MIMO antenna systems. Soitec's GaN engineered substrates are ideally positioned to enable compact MIMO antenna system designs even up to millimeter wave bands. Soitec's gallium nitride technology toolbox has at least 2 variants to choose from. High-end gallium nitride on silicon carbide for ultimate power levels, which is used in most demanding applications, and the mainstream gallium nitride on silicon for cost-sensitive, large diameter, and high-volume markets. Gallium nitride on silicon technology still has far superior RF performance compared to gallium arsenide or silicon-based technology. We offer optimized structures for both sub-6 and millimeter wave applications, either on silicon carbide or silicon substrate. And then our customer can further decide to differentiate their product design by customizing the barrier and the cap layer for their specific application needs. We indeed offer a variety of barrier layers, like aluminum gallium nitride, which is most industry standard, indium aluminum nitride for low sheet resistivity, or aluminum nitride for very thin barrier. This combined with standard gallium nitride or in-situ silicon nitride caps, you can tune the barrier composition and thickness, and this will enable you to reach the ultimate performance, especially for millimeter wave applications. Especially the deposition of an in-situ silicon nitride passivation layer directly after cross will seal the gallium nitride epi wafer, passivate your surface state, and then also further facilitate the entrance of the gallium silicon technology into silicon CMOS. Soitec pioneered this in-situ silicon nitride surface passivation and now applies it to much broader purposes, among them a unique gate dielectric with a smooth and contamination-free surface. Our production site is located in Hasselt in Belgium, where we focus to produce the best gallium nitride heterostructure for the specific customer application, both on silicon carbide up to 150 millimeter or on silicon up to 200 millimeter. In order to fully develop the strong value proposition of gallium nitride for power amplifiers, as you can see summarized on the right side of the slide, both for the sub-6 and for the millimeter wave range, Soitec continually extends its product roadmap, both in terms of wafer diameters, either on silicon or silicon carbide, as well as with advanced epi layer design. We will now show you our product for filters, which will be introduced to you by Christophe Didier.
Thank you, Marianne. In addition to SOI substrates and GaN engineered substrate, we also have substrates to address some very important components in the front-end module, the filter devices. So let me introduce piezo insulator, PY substrate for filters. Smart cut technology can be applied on many different types of material, and POI is our first engineered substrate based on smart cut technology that is using non-silicon material and that ramped into production. A POI substrate comprises a thin layer of piezoelectric material, typically a few hundred nanometers thick, on top of a silicon dioxide layer, also in a few hundred nanometers thick, sitting on a high resistivity silicon. The piezoelectric material is the same as the one used today for SAW filter on bulk material, namely lithium tantalate or lithium niobate. The buried oxide acts as a temperature compensation layer by constraining the piezo layer and limiting its expansion, contraction, and limiting the frequency shift due to temperature changes. The high resistivity silicon helps to reduce the losses associated with the substrate. This structure confines the acoustic wave energy in the thin piezo layer and enables a much better control of the acoustic waves propagating in the piezo material. Filter designers have now access to the right substrate to design high-performance resonators. Resonators are the building blocks of the filter design. As a result, filters on POI substrate have been developed by major RF front-end module makers, and the 150 mm diameter POI using lithium tantalate is in high-volume manufacturing today at our Benin-3 facility in France. In our roadmap, we are also looking at replacing lithium tantalate by lithium niobate. It will enable the design of higher bandwidth filter, typically above 8% bandwidth. We are also developing a 200 mm POI to improve even more the filter cost of ownership. Filters are key components in the 5G smartphone front-end module, and many more filters are necessary to support MIMO, carrier aggregation, and the new 5G bands. Between 4G and 5G, we expect more than 50% filter area average growth in front-end module. .5G is also more complex, and in order to support the 5G more advanced requirements, filters have to improve beyond what the current solution allows, more specifically on frequency stability over temperature, bandwidth, power consumption, and quality factor. Filters use different design technology today. The first one is surface acoustic wave, SAW technology. But SAW filters are very sensitive to temperature and generate important frequency shifts when temperature changes. This shift is referred to as TCF, and measured as ppm per Kelvin. For SAW, the TCF is typically several tens of ppm per Kelvin. The TCF can be improved by adding a temperature compensation layer on top of the SAW. Those are referred to as temperature compensated SAW, or TC-SAW. Another more complex technology used for RF filters are the bulk acoustic wave, BAW filters. They require many additional process steps to build either a bright mirror or cavities inside the material. So compared to other technologies, such as SAW on bulk piezoelectric material, TC-SAW or BAW filter, the SAW filter on POI provides better energy efficiency, lower loss, than SAW and TC-SAW, enable higher frequency and wider bandwidth filters than SAW and TC-SAW, has a much simpler and cheaper process than BAW filters, provides smaller footprints than the other technologies, and several filters can be integrated on the same die. And it uses a similar or simpler device manufacturing process than the other competing technologies. SAW on POI today is the ideal solution to address 5G filtering needs. On resonators we've designed and built on POI substrate, we were able to measure high Q factor. For example, we've measured Baud Q above 4,000 for mid-band resonators. High coupling, for example, we measured coupling factor K-square above 8% on SAW resonators built on POI. And very low TCF, below the 10 ppm per Kelvin. Those POI substrates will facilitate the design of high-performance filters for 5G networks. When looking at those different filter design technologies, TC-SAW are traditionally used for low-band and mid-band filters, while BAW filters are traditionally targeting mid- and high-band filters. Now, for ultra-high bands, more complex structure can be used, such as LTCC, hybrid BAW, X-bar, or even integrated passive devices. The SAW on POI engineered substrate is today an excellent alternative to TC-SAW and BAW filters to address the 5G challenges. And we are seeing a strong adoption of POI substrates to address the more difficult bands in the mid and high band spectrum. In conclusion, for all the reasons we discussed earlier, SAW on POI engineered substrate is today an excellent solution to address the 5G filtering performance and cost challenges. We are seeing a broad adoption of Soitec POI substrate, and it is in volume production in our manufacturing facility. Bernard will now conclude and wrap up this session.
Let me summarize some key points that has been shared. First of all, you see that our RF-SOI substrate is an industry standard for 4G, and it will remain a standard for 5G sub-6 GHz. FD-SOI is suitable for integrated solution for 5G system on chip, and FD-SOI plus HR offers new opportunities. GaN substrate provides new engineered substrate solution for PA. So this means that for 5G millimeter architecture, they can be addressed with RF-SOI, FD-SOI, and GaN AP wafers. Finally, we present our new POI substrate, which addresses 5G filters performance and cost requirements. To conclude, I want to leave you with one message. Our engineered substrates are at the core of the solution to optimize 5G performance and total cost of ownership. Thank you very much for your attention.